All right, so hi everyone. This is my pleasure to give this first lecture on the course Dynamical Systems, Networks and Applications. So this is the outline of the course. So what we are going to talk about today is what? So we consider a network, so with nodes and edges, and within this course, at each node, we will have a dynamical system. So at each node, we have a dynamical system, and of course, each dynamical system interacts with others by a coupling term, which is represented by the edges. And so here we will try to do some math, but there is a lot of applications. There's a lot of courses on the general topic of networks. I will provide some references throughout the talk, and we are trying more to do some math on dynamical systems. So let's start with the chain network. So in a chain network, the first node here acts on the second node, but the second node doesn't act on the first node. And the same, the second acts on the third on the fourth, and the fourth and the fifth, and so on. So we will, in this chain network, we will consider that at each node, we have a partial differential equation, a reaction diffusion system, which is a generalization of the so-called Fitzhugh-Nagumo, which is well known in neuroscience context. So what I'm going to talk about is mainly inspired by this paper here, which goes back to 2012 and is a work co-authored with Professor Aziz Alawi. All right, so let's have some look at the math before going further. So generally in the Fitzhugh-Nagumo, the function f here is a cubic. So here we generalize a little bit and we allow f to be a polynomial with an odd degree, but the largest coefficient here, the coefficient corresponding to the higher degree, must be negative. All right. We also consider Neumann boundary conditions. A, B are positive coefficients. D is positive. Well, in neuroscience context, dV is 0. And in what we are going to do, actually A, B, gamma, and mu could depend on X, on the space also. So any questions? Comments? Are you good with that? So if you want to ask a question in French, if you are more comfortable, you can do that. There's no problem. All right. So as I said, we are considering a chain, and so we consider n Fitzhugh-Nagumo equations. And as I said, the first is independent. There is no coupling terms here. But the first is acting on the second on the third, which is represented here by those conflict terms. All right. Okay, and what I want to talk with you, it's we are considering the synchronization phenomenon. So here we say that a node Si and a node Sj synchronize if the difference of their norm in L2 is going to become 0 as t goes to infinity. So this quantity here is called the synchronization error between Si and Sj, and we will say that the whole network synchronizes if this quantity here goes to 0. All right. So far, so good. No questions? All right. So just a flavor to emphasize that at each node, we have a PDE. So we can have that solutions can do something very interesting. For example, at each node, you can have these spirals. You can also go through a solution which will be periodic in time, but homogeneous in space. You can have these patterns. So you can note that these three patterns are solutions of one single PDE. It's just one PDE. The difference here is just the initial conditions. The last one here is a little bit different. You have some coefficients on the PDE which are dependent on X. They depend on X. All right, so actually this solution was inspired by some neuroscience context where we assume that some cells are not working correctly, and so the electrical signal doesn't go smoothly through the whole domain. All right. So this slide here, I repeat, was just to emphasize that at each node we can have inhomogeneous phenomenon in space, which is a big difference with networks of ODEs. So the point here is to emphasize that we are considering networks of PDEs, which have inhomogeneities in space. Okay. All right, and so here you can see that. So if we consider, for example, the chain network with 3 nodes, which is right and right here, you can see that for alpha 2 and alpha 3, large enough, all the solutions looks alike. They looks the same. And if you have a look at the synchronization error, you can see that around like time 10, it's near 0. So we have synchronization here of patterns, right? So it's the master, the first node is the master of the network, and it will give the dynamics. All the other nodes will adopt the same dynamics than the first node. Is there any question?
Please, just one little
Yes.
question.
Yes.
I want to just know if, for example, the synchronization error, if it is big, I think the solution will be different, not like this.
Yeah, that's what I'm saying. So here, at the beginning, you can see that the synchronization is large, but you're right. What we plotted here is for large T. I think here we plotted this is the plot for T equals 200. So it's 0. Of course, at the beginning, they were not the same. So you're right. This corresponds to almost 0 synchronization error.
Okay, thank you.
All right. Yeah, so thanks for asking. So we have this theorem. So we denote by m the maximum of the derivative of f. And if we assume that for all I be looking to 2 and n, if alpha I is greater than m, then the chain network will synchronize. And so we are going to prove this theorem. All right. All right, so we are going to prove this theorem. So what do we have? We have this chain network. So without loss of generality, I consider these equations. All right, so how are we going to prove that? So basically, we consider a Lefner function, but so let's give some details. So first, let's look at this function. So we're going to write V2 is going to be A epsilon yes, but of course, what I want is not that, but this one. Okay, now if I look at the derivative of that of V2, what do I have? So I have that. Plus of course I forgot that. So now what is u2 minus u1? If I take this derivative, what do I get? And so I put this a and this epsilon here. It will be f of u2 minus f of 1 and then I have so here appears the coupling term. So if I do u2 minus u1, and I take the derivative, I obtain that. And for v2 minus u1t, I get I u2 minus u1 minus b u2 minus u1. All right, so if I multiply by u1 minus 2 this quantity, and this quantity by u1 minus v2, what do I obtain? I get so look. So here, so this term here will be multiplied by this quantity, and this term will be multiplied by this quantity. So this will cancel. All right. So when I do that, these terms here will cancel. So what do I get here? I will get 2a integral of and the last term is the coupling term, which will be of course, to be precise, I get that. All right, now, this means what? This means that, so, the derivative of v2 is 2a. Now, this integral I can write it as so I can just write that this will be a number. Exists a number which belongs to U1, U2, and I call it theta 2, such that we have this quality. All right, and then so we have stir and this one minus z integral all right, but this is less than m. So finally, we have that is less than 2 u2 minus u1 squared minus b integral all right, so if I can always do that. So this will be less than 2 times delta V2 where I choose delta to be the minimum between we have that, right? So which means that we can write, so we have V2 prime which is less than delta V2, and then I can write that exponential Oh, and I have a minus, so it's minus here. So this is minus, so I can write 2. I can write that all right, which means that if I integrate that between 0 and t, I get so I have an exponential decay for V2. Yeah. So this is the main idea of the proof for synchronization. So here I only considered V2. So now, if I consider general VI, the proof will be almost the same, but so VI is what? VI will be here. All right. So the proof goes almost the same. The difference is for the coupling terms, because if I look at this term, so I will only write the coupling term, I will get alpha minus u minus 1 minus alpha u minus 1 minus u minus 2. All right. So I'm not going to write all the details for that. Just the idea, how are we going to solve that? So by using Young inequality, we will get the solution. Why? Because if I look at the derivative, I will derive this Lyapunov function here. If I derive that, I will multiply by this quantity. So here I will get actually we have that, right? And here we have that, and then when I take the derivative, so this is good because I will get minus this quantity, square, but then I have the same here. All right, but by playing with Young inequalities, we will split this term in two, and I know that this quantity goes to zero. You know, it's an induction argument. We did it for V1 and for V2, sorry, and then when we run it for V2, if we do it for V3, we will have an exponential decay with that. So by playing with Young inequalities, this term will go to zero with an exponential decay, and then we keep this term, but if you choose the right coefficient, we will be good, because this will make things close to zero, and this can be cancelled out by this term. And this is the idea. So if you want to go into more details, you can just have a look at the papers. All right? So, all right, so we have proven this theorem. But so we can do the same for more general networks. So we consider the same Fitzhugh-Nagamou equation. And with these general coupling terms. And here we will need this definition. So for a given couple of nodes, I define the minimal path joining these two nodes. For example, the minimal path joining 1 and 4, I define it to be 1, 2, and 2, 4. Now, for each edge in the graph, I will define this coefficient alpha KL as the sum of the length of all the minimal paths going through this edge. For example, here, alpha 2, 3, how many minimal paths do I have? Well, I have the path which goes from 1 to 3, which has a length of 2, and I have the path 2, 3 joining the node 2 and the node 3. So alpha 2, 3 equals 2 plus 1, which makes 3. Okay, and then with this definition, we can prove the theorem for a large class of networks. And we can prove that there exists a constant m such that if for each edge KL, this inequality holds, then the network synchronizes. Well, the proof goes as the proof that I done on the blackboard, but we need to, so for the chain network, we add an induction argument because, yeah, when we deal with chain networks, it suits that. For more general networks, we use this definition of alpha KL, right? And for example, for fully connected networks, which has an example of general networks, considering the theorem, alpha KL is 1. For each couple of nodes, we have only one minimal path, which is the path connecting these two nodes. So alpha KL is 1. And then we have this theorem. Here are numerical simulations for fully connected networks, and this curve is interesting. As you can see, so we have considered here 20 up to 20 PDEs. So this is a network with up to 20 PDEs. As you can see, here in the y-axis, we have the complete strength at which the system reaches the state of synchronization. And this is a power law. So this is of type m over n. All right. So this means what? This means that this number, which is just a sufficient condition, it's in good agreement with numerical simulations. All right. And so here is an example of synchronization of fully connected networks with there was here 3 equations, as I guess, yeah, three nodes. So for one value of the coupling strength, we don't have here synchronization. You know, these patterns are not the same. Those one are not the same. Here is the error of synchronization. They are not the same. Here, for example, here, you know, there's a difference. They are close, but they are not the same. Here you have a difference. And here they are the same. Here the error of synchronization has reached 0. All right. So you can do the same for ring network. So we have also the theorem, but then the coupling strength needed for synchronization is of n² type. And we have also a theorem, and it goes well with numerical simulations. So I didn't give the detail of the proofs, but if you want to look at the details, you can have a look at this paper. All right. Okay, so now I'm going to talk a little bit about random networks. So this is a very classic, so I'm not going to give so much details about that. You have numerous references. And so at the end, I will also give an example of neuroscience network, which is a random network. All right. Yeah, so you can, so I recommend this book from Barabazi. You can also have a look at this one from Neumann, sorry. So a random graph is obtained by you choose n nodes and you add successive edges between them at random. So a very well-known random network is based on the work of Erdos and Renyi, and actually there is commonly two Erdos-Renyi networks, the GNP, which was first introduced by Gilbert in 1960. So how do we construct this network? So you have n nodes, and then you go through all the couple of nodes in the network, and you made an edge between node I and node J with a probability P. So this is the algorithm to generate Erdos-Renyi GNP network. So you have these results, and so this is yeah.
Monsieur, si vous avez
Yes.
mis J, excusez-moi, si vous avez mis la page précédente, vous avez mis pour I de 1 à 0, donc J.
So I goes from 1 to n. So n is the number of nodes in the network. All right. From I going from 1 to n, and from j going to I plus 1 to n. Yeah, so you're right. You don't need to, you can stop, you're right, you can stop at n minus 1 here. That's what you were saying? Or? So yeah, a minus 1 is missing here. Okay. But basically you go through all the couples of nodes and you put an edge with a probability P. All right. So then well, you can prove that. It's these results are basic probability. So I refer to the books that I presented before. So this is the probability that a network has exactly L links with within the procedure. The probability that the network has L links, L edges, is given by this probability. Then the mean is this comes from the binomial law, and you got that. Then the probability that a given node has k edges is given by that, and the mean degree, the average degree, so this we call it degree, is also p times n minus 1. Okay, one of the property is that you can prove that if np is a constant, here this quantity converges to this one, and which gives a Poisson distribution. All right, so what time is it? So I'm not going to spend much more time on that. This is very well known, just a few key points. So then instead of applying the algorithm, you can also fix the number of nodes and the number of edges in the network and choose randomly the connection between the nodes. This was, for example, considered in Ardos 1959, but I'm not going to give details on that, just the story. So the problem with that is that there is a property that we know known as the small world. So I quoted that from the book of Barabasi. The small world phenomenon, also known as 6 degrees of separation, states that if you choose any two individuals anywhere on Earth, you will find a path of at most 6 acquaintances between them. So this means what? This means that you are far, even you are in France or United States, you are far from 6 ants from Biden, from President Biden. Okay, and one of the lacks of the Erdos-Renyi model, it doesn't have the small world property, neither local clustering, meaning that some group of nodes will have more links between them than other networks. So if you want, you can observe in some times networks of networks. And also a lot of graphs have a power law degree, meaning that the probability of a node to have k edges decreases as 1 over the k with some power. Okay, this is known as scale-free networks. Okay, so the Erdos-Renyi model doesn't have these properties. So Watts and Strogatz provided a model to construct a network which satisfy the property 1. So what's this algorithm? You consider a regular lattice, for example, a non-director ring. I will make a picture of that, if I can find that. Yeah. For example, let's consider a ring with nodes. Okay. So then, for example, let's say here is node 1. So you have here an edge between node 1 and node 2. So I consider this edge, and with a probability p, I will rewire why I cannot? Sorry. Oh, I don't know why I cannot. Let me see why I cannot erase. Sorry. Oh. Okay, I don't know. I'm not able to erase. Well, okay, it's not a problem. So what I'm going to do, I will rewire this node with a probability p. So, and then let's, at random, I put this node like that. All right. Then maybe this one will stay because the probability this edge was not chosen, etc., etc. And then maybe you will drop that one, and maybe you will go like that. Okay, and so this was published in 1998 in Nature.
Merci, on est là, on vous écoute, on est là.
Okay. Okay, and then so this gives the small work and clustering, but not the polar distribution. So then okay, then so came the Barabasi-Albert model. So then you will increase the nodes of the network. So you start with n0 nodes, and you connect it with some m with a probability which is proportional to the degree of which node. So the more you are connected, the more you will be connected. It's like a website. If it has a lot of connections, the probability is large, then you will get more. It's like the richer you are, the richer you get. All right. Okay. So now I will finish this first lesson with an example in neuroscience context. So it provides an example of a random network, but which is different than the ones that we have seen. And so this is a paper which is on arXiv, and it is under review. So you will consider here, this is a general model. You consider a network of ODEs relevant in neuroscience. And so what is the topology? So regarding the topic of this course, it's important to give some details. So in this model, you have two kinds of nodes. The nodes are not all the same. You have excitatory neurons and inhibitory neurons. So this network has nodes which you classify into two categories, right? So for example, in the paper, you have 500 nodes, 375 are excitatory and 125 are inhibitory. And then for each node, you pick up randomly a fixed number of E and I presynaptic neurons. So the network is directed. There is a direction in the edges, but each node can receive a large number of edges. So for example, in this paper, we considered these numbers. So for example, for each E neuron, we chose 50 among the 375, and we connected to the neuron 50E. And the same for the I, so EE, EI, IE, II. Okay, another thing is that then each node is an ODE, but this ODE has a stochastic drive. All right, so in neuroscience context, so you have a drive which might be some stochastic, some noise, but it might also be some information that you get from your environment. And then you have a recurrent activity which comes from the coupling within the network. All right, when you have that, what we consider, so this is Hodgkin-Huxley type equations. So the drive is a Poissonian drive, okay, meaning that at some times you will receive Dirac impulsion. So the GE, what is the GE? So the GE, this is variable, it goes to 0, but sometimes it gets a discontinuous impulse, which may increase by SDR over tau E, right? And the average time between two impulses is given by a parameter, okay? And then this comes from the network. So when a neuron crosses a threshold, it will induce some kicks in all its postsynaptic neurons, meaning all the neurons that are with which it connects. All right. Okay. So I'm going to be a little faster because I think you're tired and you want to have dinner. Okay, these are the results. What do you observe? You observe that when some parameters here, this coefficient here for E neuron, so each neuron I repeat can be either E or I. So for Q equals E, you have SEE. And for the, so we found that the more efficient parameter to reach synchronization was this SEE. And so when you increase SEE, this is the spikes generated by the neurons. And when you increase SEE, you observe some kind of synchronization, which is not exactly the same that the synchronization that we talked at the beginning of the presentation. But you observe that they all spike at the same time. All right. So I summarize that by a path from stochastic homogeneity, when it's hard to observe something, to partial synchronization and synchronization, where you observe very distinct events, and all the neurons will spike within an event. A partial synchronization is a regime where you observe it here. You observe some events, but here you have an event, but not all the neurons of the network will spike. So another phenomena which is remarkable is that you observe this correlation between the conductances GE and GI. And of course, you have some rhythm in the network, which might be distinct from the rhythm from each neuron, and which leads to the so-called gamma band frequency, which is 40 spikes, 40 events in 1 second. Okay, so that's what I wanted to talk with you with this first lecture. So I'm giving you some references here. And so if you want to obtain a grade for this course, I propose you this homework. You can choose any of the articles that I have mentioned today, or try to simulate networks of PDEs with random network of your choice, and do something, and then you present that to me within a few weeks, and I will give you a grade. Okay, so thank you for your attention.